Perfect.
This one.
Yes.
Okay. So, he's presenting on that?
Yes.
Okay.
Perfect. I think you can start, Deepak.
Okay, just 1 second. I'm just putting the charger. All right. Okay. I hope I'm audible now.
Yeah, we can hear you.
Okay, cool. Thank you so much. Thank you for having me. And in today's talk, I'll talk about the kind of challenges and issues that come up when we try to scale robot learning. Okay, so I think this has been a big question in at least in robotics. What is the role of learning? And in my opinion, there is only one reason for using learning, and that is to generalize. To generalize to variety of tasks and variety of scenarios. So not building robot that can do one task in many scenarios, and neither building robot that can do many tasks in one scenario, but many many different tasks in many different scenarios. Now the main magic sauce that we have been seeing in AI successes in the last several years has been really simple, and the recipe has been that you collect large data set for the end task that you're interested in, whether it's vision, speech, language, robotics, and you train large expressive models on this data set, and then sort of magic happens, like whether it's GPT models for language, whether they are models for speech, vision, etc. This recipe has been applied to every domain in the last several years where there is data, right? The same recipe for language, vision, speech, etc. And in robotics, we know that this is not exactly applicable because there is no data on the internet. So we cannot go out and collect billions and trillions of examples. Just to put this in perspective, like the scale here is really large scale. For instance, GPT-4 is trained on 30 trillion to 100 trillion tokens. 100 trillion, that's the scale at which current LLM models or VLM models begin to work really well. Okay, so now this scale is not possible because there is no internet data for robotics. In fact, I call this chicken and egg problem of robotics, because to collect robot data at scale, we really need robots to be deployed so that we can get data. But to deploy them, they need to work. But to work, they need data. So what comes first? Do deployments come first or robotic data comes first? And this is where robotics has been stuck in this problem of data for a long while. And we see a lot of demos around the systems, very engineered map systems. But again, this is very difficult to still transfer them to a variety of new scenarios in the open world. But most of all, it is very slow and expensive to collect real world data at scale, despite having despite having cheap robots today. Real world is too slow to scale to millions, billions, or trillions of examples. Now, one argument that is often given in robotics is that the idea of transfer learning. Can we use these pre-trained language models and use them to somehow solve robotics? Like use them as pre-trained model for VLMs, VLA, etc. All these models. In fact, we had some role to play in trying to popularize this direction. About 3 years ago, Peter Avil's group and my group, we wrote this paper together where we tried to see, do these language models capture information about planning at all? So this paper is called Language Models as Zero-Shot Planners. It came out before the SECAN line of work, etc. What we did is very simple. We took the scenarios like the simulation task like virtual home, AI to Thor, etc. And in these tasks, you are given a goal like browse internet, and the robot has to go to a different room, open computer, and do all of that. Now, traditionally speaking, people call this long horizon problem. And what we are trying to show in this paper is that when you abstract away all the low-level actions, then it is no longer a robotics problem. So what we show is that by simply having language models and by prompting them with examples of how to solve tasks, they can output sub-steps of subtasks, which you can then execute in these simulations to achieve this task. And in fact, in this virtual home scenario, we almost solve the whole benchmark without using any data from the benchmark itself. purely by language models. So in our opinion, this paper was more like a satire. It was a satire to argue that if you abstract away control, if you abstract away low-level motor control from robotics, it is no longer a robotics problem. It is a language problem. So even LLMs can solve this problem very well. But accidentally, it led to the whole area of barrage of papers in this area, where people you somehow get low-level skills for models, and those skills you can get by imitation learning, you can get by control design or any other way, and then you try to hook those robots up with these language models and you run them for end-to-end planning. And this is a very famous area now, of course, all this VLA, VLM models, etc. But largely, if you still look at most of this tasks that are done in these scenarios, although robots can understand complex language, but that part is nothing special about robotics. Language part is coming all from these language models like GPT, etc. The actual part, the skill, the motion, it is still very simple in most of these scenarios. Like when you say, look at these results, they are mostly about pick up a red block, put in blue box, put the red napkin in red box, like things like that. The actual skills are very simple, although language is complex. And if we talk about this, go deeper into these skills, these robotic skills, there is a lot of focus about imitation learning, large-scale learning, but the skill complexity has not really gone up in the last few years. In fact, I want to argue that I want to highlight this paper from Ken Goldberg's group from 8 years ago called DexNet. This was done by 1 or 2 students on a small, like 1 or 2 GPUs, not at massive scale of teleop data collection, at small scale and done through simulation. And they could already do a bunch of complex tasks 8 years ago without having any fancy VLA, nothing in the pipeline. And you can see here cardboard folding to picking objects from clutter. And I'm not even showing their best model. Like their best model has 100% accuracy across from any kind of clutter, any kind of scenario, which was a DexNet V3 that came out. Now, this is not just, if you think 8 years ago is not too old, I want to go back and show you results in robotics from like this video.
One exhibit at the Nuclear Congress in Philadelphia has the perfect formula for popular
Can you also hear the sound of the video?
Yes.
appeal. 2 amazing hands plus 1 pretty girl. The purpose of the display is to demonstrate the sensitive precision of the master-slave arm.
Now, I have to do this, I'm not getting time, but I wanted to colorize the video and change the audio to like 2024, like a modern audio style. If I did that, you cannot distinguish whether this video is from like 1957 or is it from like just 2 years ago from some conference in robot learning. Like they're doing all the crazy tasks that people today talk about in 1957. Now 57, and of course it's teleop, but the idea is this kind of methodology has been going around for a while. And 57 RAM used to be 1 or 2 KBs. It was before even personal computers were a thing, and people could do these kind of systems. And it's pretty smooth teleoperation. Like if you go on Twitter today, you will talk about people saying, oh, it's very smooth teleoperation, very nice, this and that. But look at this, lighting a matchstick. Like 1957. This is before computers used to exist. Like we have to really wonder what is happening in robotics. Now that was 57. Then we have 1960s copy demo. Like if you know about this copy demo, it's the first thesis in computer vision from Roberts. Now here the robot sees this goal image on the left and tries to build a similar tower on the right by only looking at the goal image of the cubes. Now, of course, if I had the video of this with the new colorization, this totally looks like a video from last RSS and not something in the 1960s. And in fact, forget about this, humanoids. Today we see humanoids all around like conferences, industries and everything, doing backflip, this and that. This video from 30 years ago, 1994, from Chris Atkinson, like humanoid doing all this juggling, like playing this, and here even competing against a foosball. I don't know what it's called, ice hockey, not ice hockey, like some table hockey or something, against a person and doing really well. Look at this task over here. Right now, robotics has had very rich success. We have been doing lot of cool work, but still we are not seeing robots around us, and that's the reason is generalization. And generalization of skills, not of language, not of vision, but of skills, what the robots are building, is that the main reason how robots will be around us, right? So in my opinion, the hard part in robotics is robotics. It's not language. Language can help us bridge the gap between interface with human, planning, etc. But the underlying bottleneck that prevents us from deploying robots in thousands of examples is not one of these videos of robots doing stuff. It's like the actual transferability of these skills across scenarios, across environments, right? So in fact, this led us to our famous Moravec's paradox, like hard problems are easy, easy problems are hard. And I feel like we keep getting stuck into this paradox over and over after every decade. Right now, again, if you look at all the demos and everything, the focus is largely on end-to-end learning, complex reasoning, complex language, and all that reasoning, but the skill part is largely ignored and is simple pick and place. While this is exactly what Moravec and other people found out after 30 years of work in between 1960s to 1990s, is that all this complex reasoning, language, etc., they are actually the easier part. The harder part is what humans think is easy, like motion, mobility, etc. And that's where we should show generalization pretty much. And the famous example, you might all have seen this over and over, but I want to re-emphasize the whole aspect that the language component, while it looks so cool in talking to robot, etc., it's just the easier part of the problem. The hard part is the skills. Now, in this talk, I want to focus on a proposal. And the proposal is that if you are trying to train or create these large scale models, there is no data available for robotics, for robot data. So what should we do? And our proposal is we should probably look for alternate sources of data that can scale for robotics. Now, what do I mean by alternate sources? Here in this talk, I want to focus on two such sources. One is simulation and the other is human videos. Okay, this is the two areas which my group at CMU and now even at Skilled, we have been focusing on very heavily for the last several years. Okay, so let's talk about simulation first. In simulation, of course, several years ago, we had this paper called RMA. It was RSS paper. 21. Can't believe it's already been 4 years. It seems like very regular, very recent area. But here what we showed that you can train robots in simulation and you can transfer it to the real world in variety of these setups. Right? The idea was very simple and it's largely been adopted by almost all the papers. You can call this system 1, system 2. You can call this two-stage process. You can call it teacher-student process, anything. But the idea is in phase 1, you perform reinforcement learning, and in phase 2, you perform supervised learning. Reinforcement learning is performed with some privileged information, like what is available in the simulation. So privileged condition reinforcement learning, this helps you find the solution. And in phase 2, you try to distill it from all the sensors available at test time, like camera image, etc., body sensing, stereo image, etc. So phase 1 RL, phase 2 supervised learning. Okay, so we did that work and we showed that it actually scales very well. You can perform. This is 4 to 5 years ago, maybe about 5 years ago. But if you look at the generalizability of these skills, we have not gone much beyond than what was already shown 5 years ago. It was best paper award at Coral, but here the robot is operating from stereo vision to action directly. The vision branch is operating at 10 hertz. The body is operating at 100 hertz or 50 hertz. And this was 4 years ago. It can do any kind of scenarios, any kind of terrain, stepping stone, etc., like stairs. One interesting part is that the stairs for this robot are actually much higher. Look at the height of stair is almost the same height as the robot. So this is not like how humans climb stairs. This is more like how humans climb walls, because the height of the body is the same height as the stair itself. And this was all from end-to-end vision, no mapping, no planning. You are directly taking the stereo image, stereo vision as input, and from that you directly output command to the motors. Fully end-to-end, operating at different frequencies, the vision branch, the control branch, no hard coding, no mapping, no planning of any sort. And it got Best Paper Award as well in that area. Now you can scale the same ideas to humanoids as well. It doesn't have to be, now this is not the latest result. I'm showing this a video from last year. So a super robust application of these ideas. Again, the same stereo vision idea from quadruped to humanoids for dealing with stairs, different height. You can apply it to whole body control systems as well. Like here, you are only commanding the arm end effector to go down and the body can bend automatically. Right? You are not pre-programming how the arm should go. This was the first paper on the whole body control, the deep whole body control of the whole robot. Here you are only commanding the end effector, and everything else is done by the model. So this is all trained in simulation with that two-phase approach I described, RMA-like approach. We improved it over time, but that's the basic idea. This is the same thing you can do from humanoids to parkours. Again, only from stereo vision, and you can see on the top right. Let me move my. Sorry, my video is hiding the thing, but you can see here this image on the top right is the image robot sees. That's the only input. This stereo RGB depth image is the only input to the robot, no, nothing else. And these are not like lab results. You can apply to a variety of robots. This is again 4 years ago. You can apply it to different kind of humanoid hardware. I already showed one or two earlier. You can also apply it to manipulation. So what I'm trying to show here is simulation as an area to scale robotics data really is a promising direction. And in the last 4 or 5 years, it has really seen transfer across areas from manipulation, locomotion to mobility. Here, this policy was trained completely in simulation. And you can notice here, it can account for errors, which is not possible to account for imitation learning. So look at the right video. It tries to grasp a bottle. But thumb got stuck in between the bottle and the robot, if you notice here. And the robot knows it should immediately recover it by moving it outward and then grasp it. Now, these kind of failure examples are very hard to collect through teleop, but in simulation, you can get them at scale very simply. Now, these are not just demos. We've been doing live demos around the world for the 4 or 5 years. This was CVPR. We did. Those of you who were at Coral probably last year, we did live demos of all the parkour results as well, and it works super well. Even though we had hardware issues in the first day or so. This robot is a Frankenstein robot. We took head from one robot, put body from another robot to put it together on the live page. This was Coral, etc. So now the question is, I want to focus on what is next. So far, if you're working on mobility, locomotion, and I'm seeing a lot of papers coming up in this area for Sim2Real. Locomotion, mobility from simulation, I would say is almost a solved problem. It already works really well. It works really well across industries. It works really well across academia. So what is next? Of course, the next big problem is manipulation, right? I would say locomotion almost solved. Manipulation is the main challenge. Now, when you go and scale manipulation, the main benefit of simulation is that it helps us provide scale by being safe. You can collect lots of data in simulation in parallel. Now, locomotion, these models already are trained on billions of samples to work really well. For manipulation, we'll require way more data. And this is where things get interesting. Like simulation, we can scale through parallelization, like Isaac Jim and etc. But we find out, and then if you notice a trend, it's very interesting trend in the last few years. The trend has been that on the y-axis is the number of environments people train on, and x-axis is the year. So you can see in the last, I would say 8 years or so, the number of parallel environments people use for reinforcement learning training has been increasing linearly in log space. So it's like exponential. And if you align that, you can see that this really began when Isaac Gym was released. So people really began increasing the number of parallel environments possible for training reinforcement learning through simulation. The issue is when I do that, the underlying algorithm that people use has largely remained the same. Now, when I'm in person talk, I ask which algorithm is that, but I'm sure all of you know that's PPO. In most sim2real papers, the underlying algorithm is PPO, and PPO is not only used for robotics. It's the algorithm which people use across all variety of tasks like LLMs, like RLHF. Now you have variants like GRPO, etc., but they are basically PPO with minor changes, right? The high level idea of PPO has been super successful across variety of areas. But notice that in this case, when we are scaling the environments to exponentially high areas, the batch size of PPO gets really, really high. So the idea is, if I can get more money and more resources, I can simulate more scenarios, I can create bigger batches, more number of environments. Does my underlying RL method scale? And we found out that's not true. You may, if you pick a difficult task, if you pick very complex scenarios, like complex manipulation tasks, and I'll show examples of that in a bit, which are very high DOF, high dimensional, even though you can keep throwing as much money as possible at the problem by buying as much compute, as many environments, PPO starts to saturate. Now, this is very surprising because people treat PPO as like something that already works off the shelf pretty much. If you go online, you will see a lot of blog posts that if you use the fixed parameters that people use, they usually works. So here, what you are seeing here is the performance increases and it saturates. While red line on the top is the top performance you can get if you do it correctly. But PPO saturates way early. So here you keep increasing batch size from 25K, 50K, 75K to 100K, and there is no increase in the performance, right? And the reason for that actually is very simple. It's very intuitive. Why is it happening? It's happening because the way PPO and other methods work, they are what we call on-policy reinforcement learning. And on-policy reinforcement learning basically means that when you're training these models, you collect data, and then that data is then used to improve the policy. Then you use the same policy to update the actors, and then you again collect data from improved policy, right? Now your policy is a deep network. Over time, when you collect data from the same deep network, even though you can create thousands of environments in parallel, the deep network cannot operate that differently across these environments. Deep network will still show similar behavior across scenarios. So over time, as you train your policy, it keeps getting better, but your diversity of data in your batch size also keeps on reducing because your policy is getting better. If your diversity is reducing, which means that you cannot take benefit of increasing batch size or increasing compute or increasing environments with this process. And that is the main issue with PPO. So as you sample more and more data, you will see that at high batches, as your policy starts to saturate, it's less random over time. It collects data mostly in the same area and not in the full coverage space of where you want. So the diversity of the batch goes down, and you cannot, so there are diminishing returns as to when you improve the batch size. And we've figured out it's a big issue when you're training it for manipulation problems for sim2real or large scale simulation. So how do we solve this problem? Well, this I believe it's an open area, but we have proposed a couple of directions over here which try to address this issue at the core. So this paper was published at ICML last year or this year, I forgot, sorry. It's called SAPG. So what the idea here is very simple. What we do is we take our main policy network, and we split that into multiple policies, K blocks. So you have, and we call one of them a leader policy, and the remaining are follower policies. So think of it as like ensembling. You're getting ensembling of PPO models, but this ensembling is not at test time. This ensembling is happening at training time. And test time, you will still have only one policy, which is the leader policy, the leader follower policy. So you do ensembling at training time, and you want to collect experience from each of these small PPO children policies. Okay. But the issue is PPO is on policy. You cannot use offline data. So what we do here is we look at the PPO objective and we change it to account for importance sampling from data coming from different children policies. So basically what you are doing here is you are doing off policy update of on policy PPO. And the off policy update is coming from other children policies of the same leader policy. So I'll skip the math over here in the interest of time, but it's a very simple change to PPO objective. Basically one line change in the code. At a high level, now instead of running one PPO across a very big batch size, which we know will lack diversity and cannot take benefit of increasing batch size, but we divide it into multiple small PPO policies. One of them is the main leader. They all run in a subset of the environment. So if your batch size, if your number of environments is, let's say 1 million, you have 10 policies. Each policy gets 100K environments. Now, across the policies, these are all different networks. Their weights are not shared. So their experience can vary from each other over time. So what you do is then you collect the experience of all the children policies, and then you apply importance sampling to update the on policy PPO as leader. And in the end, you discard all the children policies and you only use the leader policy. And that's your final answer at the very end. We made it super fast by doing some simple tricks. So it's only 9% slower than PPO, but it can get much higher performance and it can take benefit of increasing batch size with almost no issue in the wall clock time. So that is very impressive in that way. And in the end, you are training only a single policy as output. So there are also, we do tricks about, there is no extra communication overhead for GPU training. You can do multi-GPU, single GPU, does not matter. It's a drop-in replacement for that. Now, to go to experiments, here are some of the examples. So what you are showing here, so we are showing simulation here, but you can assume if sim-to-real transfer works, the result in simulation is also believable. So here, this is a 7 DoF arm. The robot hand here is 16 DoF. That is equal to 23 degrees of freedom, which is more than the degrees of freedom in a humanoid. So this setup already is more complex than a humanoid robot I showed earlier, the unitary robot. Here, so this is all trained from end-to-end RL without any fancy reward function, only changing the optimization from PPO to SAPG. Here, the robot has to pick up the cube and align it to this direction. This is simpler. This is my favorite one. So here, notice this. The robot has to pick up this cube at the bottom, but then has to align it to match the goal location at the top. Now, this goal location can either be given to the left arm or the right arm. And now this whole system is controlled by the policy. This is 46 DoF system. So whenever the goal location comes on left arm, it can do that. Then it throws the box to the right arm. So you have to coordinate the throwing, you have to coordinate picking up, you have to coordinate turning, you have to coordinate reorientation, arm movement. So it's a fairly complex reinforcement learning problem. And if you have done RL for sim-to-real end-to-end, getting this kind of task to high performance is very, very difficult. And in most cases, people resort to reward tuning, they resort to human demonstrations. But turns out the issue all along was PPO, the underlying optimization in these methods. Look at these plots, for instance, ignore everything. Let's look at only one example over here. The first plot. So here, if you notice, at the very base is like PPO, the orange curve. If you run PPO, you may be getting zero reward function for a long time, and you may keep thinking that your reward function is bad, your demos are bad, but turns out the underlying issue is the algorithm, the PPO itself. So if you run PPO for a long time, it does not improve. But with SAPG, we can do much higher rewards very quickly and learn very, very fast. Now, this was the paper we released in ICML earlier this year, but we already have a follow-up to that, but we call evolutionary policy optimization, EPO. In this work, what we do basically, we can do now much more complex tasks, all trained from scratch from in simulation with very high batch size. But the difference is now instead of having 5 follower policies, we have 50 to 60 of them. We found out that more follower policies we have, the more stable it becomes over time. So the variance decreases and the performance increases. So here now EPO can perform not only outperform PPO by large amount, but SAPG, etc. by huge amount as well. But note that this outperforming thing is only happening in complex enough scenarios. In simple scenarios where PPO can find a solution, where diversity is not an issue, over there PPO matches EPO. But in complex scenarios, these methods work much better in these setups. Oh, sorry, I don't know, the time is, I'm running late. So here we apply these kind of ideas to also perform motion planning. Here, this is all trained from end-to-end simulation, but for motion planning problems. So here, it's a sim-to-real transfer. This is what we call this paper is a DRP. It's a deep reactive policy. It's a motion planner, but it's distilled into a neural network. So it doesn't have explicit planning. It's all trained from sim-to-real or through similar approaches, but for motion planning methods from point A to point B. I don't have time for the remaining half of my talk, so I just go very fast in the interest of time. But my other half was supposed to talk about videos because humans don't explore from scratch. We also learn from videos. Now, videos, it's not imitation learning. I mean, watching by watching humans perform tasks. I call it learning by watching. And here we have been studying the problem of affordances. Like instead of using video models to make predictions, we use these models to extract how people move in the scene, like affordances, and then we use that model to transfer to robots. Now, Sim2Real is providing low-level control of the robot. This is providing mid-level control as to where to go in the scene and how to operate. It's a very simple idea. Just to show the idea in 1 second. You look at any human video, you track human wrist and human arm, and you find when the human arm made first contact with the object, and then you track the wrist movement, and that tells you how the human wrist moved. But since the contact with the object was made earlier, you get a feedback of how should that object move in the real world. So this is the idea of affordance. So we can train all these affordance model completely from videos without any supervision from outside, purely unsupervised. And then you can transfer them to new objects, unseen scenarios. And these models can already tell you ahead of time as to where should you pick the object. This is the handle, this is the cover, and which direction you should move it to open the oven, cabinet, etc. And it's only fully transferring from just human videos without any other supervision from outside. Yeah, and we can also use this affordances as a space for world models. Here we train a single world model that can control all these tasks together. The volume is a bit high. So here all these robots are all controlled by the same world model, and this world model was shared between human videos and robot videos. Since human videos don't have action, we use affordances as the action space for human videos. Yeah, I just skipped this, but we found that the more data you use from passive examples, the higher the performance is. So pre-training from human videos really helps you learn faster for downstream tasks in these setups. We have been also trying to scale it to human hands. So this is training on YouTube videos. The more you train, the better the human hand aligns with the robot. And there's a leap hand example. Now, many of you may have already seen leap hand. We have a leap hand V2 version coming. Kenny is showing live demo in RSS already at the booth or poster. But we are trying to find scalable methods not only from simulation videos but also to collect data through teleop. Now, of course, we know teleoperation has been like very scalable approach. It's not very scalable for data collection, but it's very widespread right now because of you can collect high quality data. But in RSS, we have an upcoming paper which we call DexWild, where we do the similar. We try to maintain the high quality of teleop system, but at the same time get diversity and speed of human videos. So we create, this is one last slide. This coming in RSS, so you can check it out. But here we created this glove and a camera system where you can just scale data with variety of scenarios and variety of environments. Sorry, I'm just going fast towards the end. But eventually the idea is you want to combine data from teleop, videos, etc., and put them all together. So this is all from combined from videos plus DEX file setup for variety of tasks like handover task, T-shirt, etc., in these scenarios. But anyway, just to summarize, so today I focus primarily on simulation, how simulations are powerful and what is still missing in trying to bridge the gap between simulation and real. But simulation and videos, I believe, are the two sources of data which can really help us scale to variety of scenarios. But we have to still bridge the gap between the two by solving the problem of adaptation, either adaptation from simulation to real or videos to robots. And in all the results I showed, every robot I showed was a low-cost robot, pretty much. Like quadruped robots were like a few $1,000s. The hand I showed, that cost about $1,200. So I really believe if you want to really scale robotics data collection, it has to be with very low-cost robots at scale. But with that, thank you. Sorry, I've been a bit late over time.
We're running a bit out of time, so maybe one quick question.
Thank you for very interesting lecture. In terms of transferring knowledge from video to real robot to real arm, how important is to have 5 fingers? Because in your example, it was 3. How it's transferable? Can you describe?
This is a very, very, very good point. I don't think 5 fingers are really necessary unless you are doing very power grasping task, like where you're trying to hold something with your hand very tightly so that somebody can snatch like a long stick. Apart from the very power grasp, like you can do most tasks with just 3 fingers. In fact, in the leap hand, what I showed, we actually have 3 fingers and 1 thumb. So thumb is very important. You can have 2 fingers, or I feel like at 2 fingers, it starts to cap out. 2 fingers, 1 thumb is already very good for doing several tasks. 3 fingers and a thumb is, you can do almost all tasks which a full hand can do. Unless maybe things like playing musical instruments, etc., where you use the pinky finger for something. But otherwise, we have not found that that pinky finger is not the limiting factor in most, unless for power grasp or musical instruments, in most scenarios. But that being said, you can do a lot of things even with a parallel jaw gripper. And what we are missing in most scenarios is the model and the robustness and generalization, and not really the hardware at all times.
All right, we're out of time. Let's thank Deepak one more time.